Alright, we are going to go over this explosion problem with momentum and then friction. During the explosion, friction is negligible. Negligible means do not use it, do not include it, that the force of friction is equal to 0. If m2 moves at a speed of 2 meters per second after the explosion, find the speed of m1 after the explosion. So when we look at this explosion, this needs to make us think that this is a collision. And so what we know during a collision or an explosion is that momentum is conserved. And so when we say momentum is conserved, we mean that before and after the collision, the momentum of the system has to be the same. So if we're trying to find the speed of one of the objects after a collision, we want to start off by drawing our before and after picture. So what are both objects doing before they collide? What are both objects doing after they collide? So the before picture is provided for us. They're both at rest. So we've got object 1 and object 2 that are both not moving. 5 kilograms and 1 kilogram. When they explode, they'll explode away from each other. What that means is that object 1 is going to move to the left, object 2 is going to move to the right, and because the momentum was 0 beforehand, the momentum has to add up to 0 afterwards. When we're setting up this problem for conservation of momentum, we're going to say that the momentum of object 1 plus the momentum of object 2 has to equal the momentum of object 1 plus the momentum of object 2. Before the collision, they're moving together as one object. We could add their masses. m1 plus m2 are all moving together at this original speed. And after the collision, they separate. So m1v1 plus m2v2, we have to take care of the momentum of each one separate and then add them together. And so we could put in here 5 plus 1 times 0. It's just going to start off with a momentum of 0. And then this 5 kilogram block is going to move to the left, and this 1 kilogram block is going to move to the right. And let's go ahead and define that to the right is our positive direction here, and to the left will be our negative direction. It tells us that m2 moves at a speed of 2 meters per second. So m2 is moving at 2 meters per second after the collision. And what we're trying to find is v1. How fast is the block 1 going afterwards? So we've got 5 times v1 plus 2. And so now we'll have to subtract 2 over. And we're going to get that v1 is negative because it's moving to the left. 2/5 is 4/10 is 0.4, so negative 0.4 meters per second is the velocity. If it asks for the speed is equal to the absolute value of the velocity. It's called the magnitude of the velocity. So the speed would just be 0.4 meters per second. Now for part B, after they start moving, friction is no longer negligible. They have friction acting on them now, and they give us mu s and mu k. So it says draw a force diagram for each mass after the collision while friction is acting on them. So these two masses have now hit a rough spot where object 1 is moving to the left on rough ground, and object 2 is moving to the right on rough ground. And so when we draw their force diagrams, we're going to say that object 1 has a force of gravity down and a normal force up. And because it's moving to the left and there is friction, friction is going to oppose the motion. And so friction is going to be acting to the right. Then if we look at object 2 is going to also have a force of gravity going down because it's on Earth, a normal force going up because it's on a surface. It's moving to the right, and it's got friction acting on it, but friction is going to oppose the motion. And so to oppose the motion, friction on this one will be acting to the left. Okay, so we have done part B, which was to draw the force diagram. Part C is to find the acceleration of each mass while friction is acting on them. And so if I'm looking for acceleration, I can basically find acceleration in one of two ways. I could either try to use my kinematics equations like the shovel, plow, and bulldozer, or I can use A equals F net over M. And in this case, if I'm looking at my forces and my force diagram, and I don't know a lot about, I know their starting velocities, but I don't know a lot of other information. I think I'm going to start here with this force diagram. And so for mass 1 has a net force of the force of friction acting on it. You can see that the normal force and the force of gravity balance, and that the unbalanced force acting on it is friction. So when I'm solving for the acceleration of block 1, I need to use the net force acting on block 1 and the mass of block 1. And so the acceleration of block 1 will be the force of friction acting on 1 divided by the mass. So now I need to solve for what that force of friction is. And force of friction is equal to mu times the normal force. And because it's moving, the fact that it's moving means that we're going to use kinetic friction. This is mu k, and this is force of kinetic friction acting on it. And so now I need to know what the normal force of this block is. So I'm going to say that the normal force of 1 is equal to the force of gravity of 1, which is equal to m1 times g. So m1 had a mass of 5 kilograms. G we're going to use as 10. So both the force of gravity and the normal force are equal to 50 newtons. And we did that so we could find the force of friction. And so looking back up, it says that we don't need this one. We need this one because we're moving. 0.3 is going to be the value we use here. 0.3 times our normal force is going to be equal to the force of kinetic friction. So we'll do 0.3 times 50 and get 15 newtons of force of kinetic friction. And so that's how much friction is acting on block 1. And so to find the acceleration of block 1, we said we were going to use this equation right here. That the acceleration of block 1 is equal to that net force of friction divided by the mass. So I'm going to take that force of friction and I'm going to divide it by the mass. Turns out it looks like this mass is really canceling out of the problem. If you're one of those that needs help with variables, this is really mu k times Fn all over m, or mu k times mg all over m. Look at that. Turns out that the acceleration is solved for really only knowing mu k and g. So if I do 0.3 times 10, I'm going to get my answer here. And it's the same answer as 15 divided by 5. So both times I get that my acceleration was 3 meters per second squared. And now when I'm looking at this, I was using the magnitude of everything here, but notice how my friction is to the right, and so I would call this acceleration a positive value because my acceleration is to the right, because my net force of friction was to the right. And then when I look at my object 2 here, object 2 has almost the exact same things happening on it. We're going to solve for its acceleration by finding its net force divided by the mass. And for object 2, the net force acting on it is just the force of kinetic friction acting on mass 2. And so really it can be solved for by mu k Fn over mass 2. And now again, Fn is equal to Fg here. Those two are balancing, which is equal to mg. And so I can really just do UKMG over M. And so what I'm getting is 0.3 times, instead of, 0.3 times 10. Look at that. It's the same acceleration that both blocks are experiencing. It's going to be 3 meters per second squared. But notice in this case, our friction is going to the left, and we have defined to the left as the negative direction. So I'm going to throw a negative sign onto the acceleration because the force is to the left, the force of friction is to the left, the acceleration is to the left, and so to the left is a negative sign here. All right, now I am going to find the distance of each object before it stops. To find the distance of each object before it stops, now I think I'm going to go back to my kinematics equations. How far, how fast, how long. And so with my kinematics equations, I always have that guess method. I always have to have 3 given variables, 1 unknown variable. Then I write what equation I want to use. I substitute into that equation, and then I solve. And so with my 3 given variables, let's see what I know. I know, let's do block 1 here. For block 1, we know that its starting velocity while it's sliding across friction, its starting velocity is going to be the velocity that we found for block 1 up here. So 0.4 meters per second. And really, it's got a negative starting velocity because it's moving in the negative direction. So we can say negative 0.4 meters per second because it's moving to the left. And then we also just solve for the acceleration. So the acceleration of this one is going to be positive 3 meters per second. It's slowing down. So one of these is positive, one of these is negative. We can say the velocity is negative because it's moving to the left, and the acceleration is positive because it's acting against the velocity. And then I'm looking for the distance. That's my unknown, is what is delta x equal to? And so I have to go back to the problem and say, oh, before stopping. Stopping is a tricky way of giving me a variable. That's that my final velocity is equal to 0. So I'm going to say that my final velocity is equal to 0 because I stopped. Now I don't have time and I don't need to know time, so that means that the equation that I want to use is v squared equals v starting squared plus 2a delta x. And so 0 squared equals negative 0.4 squared plus 2 times 3 times delta x. And so now I have to do some math. 0.4 times 0.4 is 0.16. I have to subtract it over. Negative 0.16 equals 6 delta x. And so divide by 6 and get 0.16 divided by 6. It's going to be that delta x equals negative 0.026027 meters. This negative means that it moved to the left 0.027 meters from where it started. Now we're going to do this same exact thing, but we're going to do it with block 2. Remember, block 2 is moving to the right, but it's slowing down. So when we list our 3 given variables here, our starting velocity for block 2, we're going to see is 2 meters per second. So 2 meters per second is how fast it was going when it encountered the friction. The acceleration for block 2, we said, was negative 3 meters per second squared, because while it's moving to the right, the acceleration is to the left in the opposite direction that it's moving. And so we have that negative sign there. This one is also stopping, so our final velocity is 0 because it's coming to a stop, and we're trying to solve for delta x. So it'll be that same equation because we have our same variables, and we don't have time or need to know time. So we've got 0 squared equals 2 squared plus 2 times negative 3 times delta x. So we'll subtract 4 over, and then we'll divide both sides by negative 6. So we've got 2/3 here, or delta x equals 0.67. This is positive because it goes to the right. 0.67. You're almost done. Find how far apart they are away from each other. So, again, a nice little picture is good. I've got object 2 and object 1 that were both right next to each other to begin with. Object 1 goes to the left, 0.027 meters to the left of where it started to where it ends. And object 2 goes to the right. Object 2 goes to the right, 0.67 to the right from where it started. And so really, how far away are they from each other now? Well, one traveled a distance of 0.027. The other traveled a distance of 0.67. Turns out I have to add those two distances together to find out how far from block 1 to block 2. So I'm going to do D1 and D2 added together to find their total distance. So 0.67 plus 0.027 is going to be 0.6937 meters.